Hi, everyone. My name is Andy Ravenna, and I'm a technical trainer at SAS Institute. Today, I would like to talk to you about how to train machine learning models both quickly and interactively. This is basically a subset or a sample of a course that we can teach for you at SAS Institute. There's going to be some links down below that you can click on to get more information if you need them. But in the meantime, I'm going to go ahead and get started. Let me switch over and grab my PowerPoint slides. There we go. And so what we're going to talk about in the short time that we're going to spend together right now is I want to give you a very broad introduction into SAS visual data mining and machine learning. Then I'm going to very quickly jump into some machine learning models and show you how to create some models. And you'll notice that we actually have several different machine learning models available to you in SAS visual data mining and machine learning. But in the time that you and I are going to spend together, I'm going to cover just two of those. I'm going to focus in on neural networks, which are one of my favorites and are really cool, and also talk to you about forests. So let's go ahead and get started. I'd like to start by giving you a broad overview or an introduction into SAS visual data mining and machine learning. SAS visual data mining and machine learning is a web-based product that's actually an add-on onto two other SAS products, SAS Visual Analytics and SAS Visual Statistics. There's actually sort of a hierarchical relationship among these three products. You're going to start with SAS Visual Analytics, and that's where you're going to start to explore your data and clean up your data. Then, on top of that, you're going to add SAS Visual Statistics, and that's where we begin to perform both supervised and unsupervised analysis. Finally, on top of that, we're going to add SAS visual data mining and machine learning. That's what you and I are going to be talking about today. And this is where we begin to start to build machine learning models, things like neural networks, support vector machines. So it turns out that all of these products are basically taking advantage of in-memory capabilities on these SAS servers. And we call this SAS Cloud Analytics Services. We call that CAS. And basically, you're going to have a whole grid of machines, a whole bunch of machines that are going to be linked together, and they're going to allow you to load up big data, and that big data is going to stay in memory. And not only does the data stay in memory, but also the analytics are performed in memory. One of the really cool things about putting your data in memory is that basically it persists and multiple people can be working off of that same one table that's been loaded into memory, and they can all be building models. And that's one of the reasons that SAS Viya is so efficient. We're going to focus in on SAS visual data mining and machine learning. And as it turns out, there's actually two different approaches we could use. We could use this programming approach or the visual drag and drop approach. So we've got these two different approaches. Now, if you and I wanted to write code, then what we could do is we could take advantage of writing either these things called CAS actions, which are sort of a more fundamental unit of code, or a little bit friendlier, you and I could write SAS procedures. Some of you may already be SAS coders, so you're already familiar with the concept of a SAS proc or procedure. Well, you and I are not going to be doing that. We don't want to write code today, even though we could. We're going to take advantage of this visual drag and drop approach. Now, actually, turns out that SAS Viya is so flexible that we actually have multiple ways of being able to do that. We could use, for example, SAS Studio. SAS Studio allows us to take advantage of these things called tasks. And while you're pointing and clicking, then SAS is going to be writing code in the background, and you can actually look at that code if you'd like to. Another option would be to use Model Studio. Now, Model Studio is very powerful because it allows you to build pipelines, And so you can create many different models very quickly. But you and I are not going to be doing that. We're going to be focusing here on SAS Visual Analytics. Remember, SAS Visual Data Mining and Machine Learning is an add-on to SAS Visual Analytics. Let's dig just a little deeper into SAS Visual Data Mining and Machine Learning on SAS Viya. Now, I've shared with you that you can take this programmatic approach or point and click approach. If you're using visual analytics and you want to use the visual interface, you have the ability to build these 6 models that are listed here. Bayesian networks, factorization machines, and forests, and gradient boosting, neural networks, and support vector machines. However, if you'd like to write code, there are additional options available to you in the SAS Studio programmatic interface. So for example, I might have a student that would come to me and say, hey, Andy, I'd like to be able to perform robust principal component analysis. That's at the very bottom of the list here. And I'll tell them, sure, you can do that, but you're going to have to write code if you want to do that. Well, you and I are going to be focusing in on this visual interface. And what I want to start with is by sharing with you how to build models using neural networks. So let's go ahead and get started. Before we actually build a model in the software, I know some of you are going to be very familiar with neural networks and some of you are going to be brand new to neural networks. So let's just talk a little bit about neural networks before we actually build one. Neural network models were originally inspired by neurophysiology and the interconnections between neurons. If you think about it, our brain is very similar to a machine learning model. It takes data in order to learn, and the more data and the better data that we get, the better the machine learning model is going to perform, just like the better our brain is going to perform. Let's think about me as a child, which was a very, very long ago, and I'm not going to tell you when that was. I didn't know, for example, the differences between apples and oranges until I actually learned that. I learned that apples were red, oranges were typically more orange in color. I also learned that apples were very hard on the outside and you could eat the skin, but with oranges, you peel them open and they tended to be a little juicier. So just like I learned that information as my experience grew, these neural networks, which are a great example of machine learning models, they are also going to continue to learn and grow and perform better with more data being fed into them. You can see here that the basic unit of computation in a neural network is the neuron. Let me point that out for you right here. So here's my neuron. Some people call this a node. And what it's going to do is that neuron is going to receive input from some other nodes or from an external source. And it is going to compute an output. So here's my output over here. Here's my input. And in this slide, you can see that my neural network is depicted with just a single neuron. And in this example, what we're trying to do is take a linear regression and view it as a neural network. So we can kind of think of that neural network as a CPU, a central processing unit. And over here on the left-hand side, if you think about a linear regression, what I have is I have my parameter estimates, all of my betas, times my input. And so what the neural network is going to do, it's the central processing unit, its responsibility is to add together the weighted inputs of these parameters that we have here. It's also going to add together the y-intercept, and then it's going to place that sum into some sort of transformation function. Now, for a linear regression, that, of course, is going to be the identity function. And then what we'll have over here on the outside, we'll have our output coming from that linear regression. Here we have an example of a relatively simple neural network. Now, just like a regression, we're going to be making a prediction. Over here is my prediction, it's my y hat. And we're going to get that prediction from this particular formula. So that prediction is going to use the values of our input variables in this mathematical equation. We can think of our neural network formula as a regression of the response variables on a set of derived inputs called hidden units. You can see in this particular example, I've got 1, 2, 3 hidden units. Let me show you what those hidden units consist of. So now here are my hidden units, and you can also see down here that for each one of these hidden units, that what it looks like is that these are sort of a regression on the original inputs. So I've got my X1 input and my X2 input. You could kind of think of maybe we're looking at the age and the income of either a patient or a customer. So these hidden units can be thought of as a regression on those original inputs. And in a way, what we're kind of doing is we're sort of doing a regression on a regression. And that's not too far away from what's going on. Now, you also might have noticed that down here, each one of these hidden units has what's called an activation function. And in this case, it's the hyperbolic tangent. Now, what that's doing for us is it's going to make sure that anything that comes out of each of these hidden units is bounded between +1 and -1. Because when neural networks are trying to find the solution, very large values cause difficulty. So we're kind of bounding that output. I also want you to notice that the components of a neural network have a very different naming convention, and that's because of our neural network's biological roots. So instead of parameter estimates, betas, what we're seeing here are these W's. So I've got a lot of W knots, and we call those weights. And then instead of a y-intercept in the neural network, we actually call that a bias estimate. And one final thing that I want you to notice is that if this was a linear regression, I would have much, much fewer parameter estimates. And so you can see, even with a relatively simple neural network, that I have a lot of weight estimates. So that neural network has to find a lot more values when it's working off of this neural network model. What are advantages of neural networks? Well, it turns out that neural networks are very popular because they're universal approximators. So if we have a sufficient number of hidden units and enough time, a neural network can model any input-output relationship to just about any degree of precision. They can handle both linear and nonlinear relationships. Now, unlike a regression, it's not necessary to specify the functional form of the model. In other words, unlike a regression, we don't need to know the relationship between the inputs and the outputs. So with a linear regression, you know, if we want to test an x squared term, we have to add that x squared term into the model to see if it's significant. With a neural network, we don't have to specify any sort of relationship between those inputs and outputs. We just basically build the model, define what our model is going to be, and it's going to be able to work off of the data. A final advantage of neural networks is that once trained, a neural network is among the fastest executing predictive models. And that means that a trained neural network can efficiently score large volumes of data. And that's something to think about if you have several options when you're trying to pick a champion model. But there are some disadvantages to neural networks. So what are the disadvantages of neural network? The big one is this lack of interpretability. Some people call neural networks black boxes, and that's because we can't really explain why a neural network gives you a certain result. Let's say, for example, that I built a neural network to determine whether a customer should get a loan or not. And let's say that the neural network denies Andy alone. Well, one of the things that's kind of interesting about that is that we can't really tell you why the neural network decided not to give me a loan. Now, let's contrast that with the decision tree. Let's suppose I had a decision tree and we denied Andy a loan. Well, then I've got a full set of rules that I can use to help explain why Andy didn't get a loan. Andy, we didn't give you a loan because you don't make enough money and you defaulted on your last 3 loans. Okay, now I understand. A second disadvantage of neural networks is that unique optimal values for weights are really not guaranteed because you might run into a local optima versus the global optima. So it's possible to run a neural network multiple times with the same data and get slightly different results. All right, let's dive in and build a neural network model in SAS visual data mining and machine learning. So I've logged into SAS Viya, which by default is going to bring me into SAS Drive. And what we want to do is go to this very upper left-hand corner menu, and you and I are going to go into Visual Analytics by selecting Explore and Visualize. That brings me directly into a brand new report where I can start to build my neural network. So I'm going to come over here to Data, and I went ahead and preloaded in a table that I'm familiar with working on. It happens to be data that is collected information over a campaign series where we kept track of whether a customer from a bank made a purchase or not for different kinds of items. For example, this bank offered loans and credit cards and bank accounts. And so now we want to be able to use that past data and determine whether a customer is going to make a purchase in the future. The primary target variable is down here. It's called target binary new product. It's actually coded as zeros and ones, where 1 indicates that a customer made a purchase during the campaign season, and 0 indicates that they made no purchase. Now, because it's coded in zeros and ones, Visual Analytics is actually storing it as a measure. So I'm going to do a right mouse button click on that, and I'm just going to very quickly convert it to a category. So now we've got that categorical primary target variable, which happens to be binary, and we're going to be able to use it as our target to make some predictions. I'm going to come over to the Objects pane and scroll down and find Visual Data Mining and Machine Learning. And here's my neural network object, and I'm going to double click on it, even though I could just drag and drop it to a canvas. And now Visual Analytics is saying, hey, Andy, you need to assign some data. Now, before I do that, I want to go up here and switch an option, which we're going to go to our interface options, and we're going to disable the auto refresh. And basically what that means is I'd like to make lots of changes before I refresh the screen. I don't want the screen to refresh every time I make a small change. Now I can click on Assign Data here in the middle, or I could go over to the Roles pane. I'm going to try here. I'm going to add in my response variable. That's going to be this binary new product. And now we want to add in our predictors or our explanatory variables. Well, we have some data here that's already been cleaned, and that's actually the 12 variables that I'm going to select here. They're continuous variables that include things like the average sales the customer made over their lifetime and the customer tenure in months. So this is a whole bunch of continuous variables. Then I'm going to scroll up to the top, and I'm also going to add in 2 categorical variables that show us an account activity level and our customer value level. You can see the cardinality of those 2 categorical variables. So the account activity level has X, Y's, and Z's. And the customer value levels are A through E, where A is the most profitable and interesting customer that we have. Now I'm going to click on OK. And now I've added in information to build this neural network. So now it's time to click on refresh. While that's refreshing, I want to show you some options over here that we could have taken advantage of. First of all, there's an auto-tune button, which is really awesome when you're building a lot of these machine learning models, because many of them have what we like to call hyperparameters. A parameter is something that you can calculate from the data, but a hyperparameter is something that you cannot calculate from the data. So if we use the auto-tune feature, we can actually get suggested values for those hyperparameters, which is very powerful and very, very useful. I'm not going to cover all of these options, but I do want to show you here we have the L1 and the L2, and for those of you that are familiar with neural networks, you know those are our regularization parameters, and they can help us find a model that generalizes well. In other words, a model that's going to perform well not only on our training data, but also on new data that comes down the pipeline. Then I'm going to scroll down just a little bit more to show you that by default, the neural network got built with one hidden layer, and in that one hidden layer, there were 10 neurons using the hyperbolic tangent activation function. So now it's time to take a look at our model. Now, before I look at our model, I am going to take advantage of one other option, which is under model display. I'm going to change that plot layout from fit to stack. And what that does is it just gives me a little bit more real estate here to work with. So here is the neural network diagram. It's we sometimes like to call these multi-layer perceptrons, because what we have here is we have our input layer, then we have our hidden layer, and we have our output layer. And you can see that as I mouse over each of these items that we get a pop-up, and we can actually use the mouse to help us drill in just a little bit so that we can get a much closer look at what's going on. Now, one of the things that I like is to take advantage of a couple of options. I'm going to come over here to the options pane one more time. And under the network diagram options, I'm going to turn on the neuron labels. And I'm also going to take advantage of taking this percentage of links to display. And I typically like to bring that down to about a third, somewhere close to that. And when we refresh, what that's going to allow me to do is focus in on those particular nodes or neurons that are more important. In other words, they have bigger weights. So it cleans up the diagram just a little bit. So you can see in my input layer down here, it looks like the count purchased over the past 3 years. So that's how many items a customer purchased in the past 3 years. Seems to be an important variable or input to this particular neural network. Now, as we take a look at this, the size of each of these circles or neurons are actually the absolute value of their weights. And then you can actually take a look down here, and we have a color-coded chart to show us whether each of these neurons is positive or negative. So here are the 10 neurons that we built. And for example, if we look at neuron number 3, you can see that the neuron average is negative, and that's why it's blue in color, but it is rather large. So that's why that circle is one of the bigger ones. And then if we came over to the orange neuron here, which happens to be number 5, and we mouse over that, you can see that that neuron averages a positive value, and that's because, and so that means it has a little bit larger effect. Now, what is exactly in each of these neurons? Well, we would have to come over to the input layer to see what helps create that neuron. And that's why these neural networks are a little difficult to interpret, because we really can't say what makes up this neural network. Let's take a look at this second tab, the iteration plot. And this is just the objective loss function, so we can see it is smoothing out towards the end as we found a solution. I think it's more interesting to do a right mouse button click and switch over to the relative importance plot, which shows how each of the different inputs are important to this neural network in relation to each other. And you can see here, just as we saw on the neural network diagram, the count purchased over the past 3 years is the most important input to this particular neural network. Also, if we do a right mouse button click, we can see the partial dependence. And partial dependence plots are very useful because they help us sort of begin to get an understanding of what each of the models are doing and how these inputs affect the output of the model. So for example, you can see this is the partial dependence plot for the count purchased over the past 3 years. And what we're seeing here is that as the count increases, our predicted probability is also increasing. So that's very interesting and useful information. Let me finally come over here to the assessment panel. By default, we're going to see the confusion matrix, and these are those 4 counts that make up a whole bunch of statistics when we're trying to evaluate a model that predicts categories for us. So you can see here, these are my true positives. So these are the purchasers that my model identified as purchasers. And over here, we have our true negatives. And of course, these are the non-purchasers that were identified as non-purchasers. And then we also have our false negatives and our false positives there. If we do a right mouse button click, we can look at the lift chart. Now, the lift chart gives us an idea of what kind of lift or advantage that the neural network gives us. The blue line represents the model, and you can see at the 5th percentile, my model has about a 3.5 lift. All right, so what exactly does that mean? It means that using this model, if I were to grab the top 5th percentile of my customers, I'm 3.5 times more likely to reach a purchaser over just picking customers at random. And hey, that sounds pretty good to me. I'm also going to do a right mouse button click and switch over to our receiver operator characteristic chart, or our ROC chart, which is another assessment plot that we like to use to help us see how well our model is avoiding misclassifications. We don't want to have misclassifications, right? I don't want to identify a purchaser as a non-purchaser, and I don't want to identify a non-purchaser as a purchaser. Now, if my model was a perfect classifier, what we would see, let me use my control here so I can, have I got a little bit? Nope, I don't have it. I don't have that red flashlight for you, sorry. What we would see is this outline of the box. So if this blue curve was so large that it went to the outside reaches of this box, that would be the perfect classifier, which means we want models that have very full curves. And this is, in general, this is not a bad looking curve. One of the other ways that we can use this, some of you probably take a look at the area under the curve. I like to use the KS statistic. The KS statistic is a measure of the separation between the maximum separation between this curve, which is our model, and then our baseline model, which is picking customers at random. And so you can use that KS statistic, and of course a larger value means a better performer. I also just want you to notice here that this ROC chart is indicating to us the cutoff at about 20%. And so wherever that maximal distance lands, it is a suggested cutoff that would work well for the model. And the reason that's important is because when I do a right mouse button click and I take a look at the final assessment plot that I want to show you, which is misclassification, you can see that right now this model looks like a much better non-classifier than a classifier. But that's because if you take a look at the options, by default, the prediction cutoff is set to 50%. But we saw a suggestion on our rock chart that said 20% is probably going to be a better fit. So when we refresh that, I think we're going to see a little better balanced of a model. And here we go. This is much better balance here. So now I can see that my true positive rate doubled to over 160,000 true positives. The final thing that I'd like to show you before I move into talking to you about Forest is if I click on this maximize button, you're going to see that there's a detailed table here available to you with all kinds of great information. A lot of times I'll have students that use this SAS Visual Data Mining and Machine Learning. They go, hey, Andy, where are all the numbers? I want to see the tables of information. And here's where they are. They're hidden here in this details table. I can see all the assessment statistics that are available to me. I can also see the values that went into the misclassification and the rock and the lift charts and the confusion matrix. So all those numbers are here in this detail table. And of course, if we want to go back to the model, I can restore that and get a nice view of my neural network once more. Okay, here I am back again. I promised I wasn't going to go anywhere. I just have a couple more slides I want to go through before we get into a demonstration of showing you how to build a forest in SAS Visual Data Mining and Machine Learning. Like I did with the neural networks, I just want to give you a high-level overview for just a minute, talking to you about exactly what a forest is in case you're not familiar with that machine learning model. Really, forest comes from the concept of, we all know that a forest consists of a whole bunch of trees. Well, that's exactly what a forest is in the machine learning world. It's a whole bunch of decision trees. We actually call that an ensemble model. When you aggregate more than one model and you create the final prediction by combining the predictions from the individual models, that's what we call an ensemble model. Now, there are different kinds of ensemble models too. Sometimes we create an ensemble of models from several different types of models. So, for example, you could combine the predicted output from a neural network or support vector machine and let's say a decision tree, and that's going to be our ensemble. But in this case, when we're talking about a forest of trees, our ensemble is going to consist of a whole bunch of models of the same type. In other words, if we have a categorical target, then we have a whole bunch of decision trees. If we have a continuous target, in that case, we have a whole bunch of regression trees. So we call this a forest. And the reason that it was created is if you work with individual decision trees, you probably already know there's an inherent instability in a single tree. And that comes from the fact when you have minor perturbations in the data that you can end up with a completely different tree. So this is seen as sort of like one of the weaknesses of working with an individual decision tree, is that sometimes we see a different set of rules come down. And if you have changes at the top of the decision tree, the parents in the decision tree, they affect the children nodes. And that's just like in real life. Whatever happens or affects the parents also happens to affect the children as well. So that's why forests were created. As it turns out, when we're creating a forest, the forest algorithm that's going to be used in SAS Visual Data Mining and Machine Learning, I like to think of it as sort of taking a horizontal subset of the data and a vertical subset of the data. So that means that forest algorithm is going to do a sampling of the rows, so it's going to grab a certain number of rows, as well as sampling the input columns, that vertical subset, for every individual tree that it makes. And as it turns out, there's a term that we use called bagging, and that's that term for averaging many trees that are grown on what we call bootstrap samples. Those are going to be when we grab samples with replacement. Now, the whole idea here is the hope that if we have this much variability in the way that we sample when we create the tree, we're perturbing that training data. And that's going to work better than just doing a horizontal subset. Gives us a lot more variation in our trees in our ensemble. And the whole idea here is that if we have more diverse trees, that's going to give us a better predictive accuracy. That's what we're looking for at the end of the day. So once again, don't forget the concept is, let's say my forest consists of 100 trees. That means when I'm ready to build the next tree, I'm going to grab a certain percentage of the rows, I'm going to do that horizontal subset, and I'm going to grab a certain percentage of the columns. Maybe I've got 10 columns and I'm only going to grab 3 randomly. And then I'm going to build that next tree. And that's one of my 100 trees. Now, when I'm ready to build the next tree, I'm going to grab another random horizontal subset and another random set, vertical subset of those inputs. So what exactly are advantages of our forest? Well, forests have some of the same advantages that decision trees do, because we know that trees automatically handle missing values as they start to grow in the tree. They can be handled in many different ways, and there's several different options of handling them. But what that means is we don't have to put as much preparation into our data. In other analyses, sometimes we have what's called a complete case analysis, where if we have a missing value, we need to basically find a way of handling that. We typically do it through imputation. But with decision trees, you don't have to pre-clean your data if you don't want to. Another thing that forests have, just like decision trees, is this concept of variable reduction. And that is, automatically the most important inputs are going to be chosen to make the splits on. And so very naturally and inherently, the decision tree, and thus the forest, is going to be able to handle and create variable reduction for us. We know if you perform a regular regression, regression doesn't do variable reduction for you unless you actually employ a variable reduction method. Well, forest is going to be able to handle it automatically. Another concept that is an advantage of a forest is that the trees in our forest are all built independently from each other, because remember, for each tree we're grabbing both a vertical subset and a horizontal subset, and that tree can be built independently of the other trees. And especially if you think about something like gradient boosting, where in order to build the next tree, you actually need information from the previous tree. That means those trees are built in sequence. Well, Viya is really been created to handle this concept of more memory. So if you've got additional memory and more trees of those independent trees can be built at the same time, they do get built, and that happens more quickly for us. Forests also tend to generalize better. Remember, what that means is, over a decision tree can get very, very what we call overfit. In other words, it's going to perform really well on the training data, but then on the validation data or on future data that comes down the pipeline, it's not going to perform so well. Well, because forests have this whole concept of a whole bunch of different decision trees, we add all that variability into the trees that we're building, and we're going to be averaging over all of that. That means that forest is going to generalize better. Finally, some people consider forest an ideal model to be compared against. So another way of thinking about this is that if you are looking at several different models, you want the models that you're looking at to perform at least as well as a forest does before you want to start to consider it. So sometimes we kind of think of that forest as a good baseline model, and then we want to be able to do better than that. There are disadvantages of forests as well. Just like with the neural networks, it turns out that forests are difficult to interpret. So once again, forest is going to perhaps give you a very accurate decision, but it's not going to be very easy to describe why the forest decided to give you that particular prediction. And that's because we're averaging over a whole bunch of trees. If we had a single individual decision tree, the rules are very straightforward. The other disadvantage of forests is that in order for you to get a really good prediction, sometimes you have to have a very large number of trees. And remember, it takes time to build each tree. So one of the things to keep in mind is that if you're trying to pick a champion model among models, you want to check and see how long it's taking your forest to actually create that real-time prediction. Okay, I think now it's time for me to go ahead and jump back into the software and show you how easy it is to create a forest in SAS Visual Data Mining and Machine Learning. In order to show you the building of a forest, I'm going to use one of my favorite features in both SAS Visual Statistics and SAS Visual Data Mining and Machine Learning. So I've come back to the neural network that we examined in my last demonstration. And when I click over here on the roles pane, I'll remind you that, remember, we created this neural network by having the target binary new product as the response variable. So that's my categorical target variable consisting of zeros and ones, where a one is an indication that a customer makes a purchase or has made a purchase in the past. And that's what we want to try to predict. Then if we take a look at our predictors, you'll see I've got a total of 12 continuous variables along with 2 categorical variables. I'm going to go to the upper right-hand corner to what we call the overflow menu, or the snowman menu. We call it the snowman menu because it consists of these 3 dots. And you'll see we have some more options here. One of the options is to duplicate as, but I'm actually going to hold down the Alt key, and now you'll see that that changes and gives me the alternative menu, which is duplicate on a new page as, and we want to create a forest. So basically what I'm doing here is I'm copying and pasting this neural network and plugging it into a forest on a brand new page. Notice when I look at the roles for the forest, it has the exact same response variable and the exact same predictor variables. And that's a really cool feature. So I can very easily create an additional model with just a few clicks. Right now, you'll notice that my forest is running. So I'm going to switch over to the options and show you what this forest is going to be created of. Let's take a look at just a couple of the options, not all of them. Notice my forest does have an auto-tune button just like my neural network did. And once again, that'll help me find good starting places for any of the hyperparameters that we're not sure of. For example, one of those would be the number of trees. So you'll see that by default, the forest is going to actually build 100 trees using a 60% bootstrap sample. So that means for every decision tree that gets built, we're going to go out and grab 60% of the data in order to create that one tree. We can see that the voting default is by majority. The splitting criterion that's used is the information gain ratio. Then we take a look, we specify how the missing values are assigned. Here's something also interesting. So our maximum number of branches is going to be 2, so we can split in 2 directions. And each tree is going to be 6 levels deep at maximum. The leaf size minimum is 5. So in other words, we have to have at least 5 observations or 5 rows in order to create a leaf. All right, I think that's enough of the options. Let's take a look at our results. I am going to scroll down and take advantage of this plot layout option where I change fit to stack, so we can examine everything on a separate tab. I'm going to go ahead and close up the options panel here and take a look. We get a variable importance table. And hey, isn't this the exact same variable that was most important to that neural network? The count purchased over the past 3 years. Well, let's take a look. We'll go back over to my neural network and let's click on the partial dependence tab and do a right click and change over to relative importance. And there it is. Yeah. So that's kind of interesting. I always think that's interesting information and perhaps useful information when we're creating several different models. We can see which of our inputs tend to be most important, and sometimes that can give us some important information that we might want to take into building our next model. There is an error plot here, and we can see the misclassification rate as the number of trees increases. So we can see by the time we get down here close to about 70 trees, it seems like we hit one minimum, and my misclassification rate does seem to be perhaps about 0.1712. We also have a KS statistic that can help us compare across models. Some people would rather use the misclassification rate. So you'll see if I click on the summary bar there, I could actually compare misclassification rates if I want to as well. And once again, there's also some additional statistics here that you might be interested in. I actually am fond of the KS and the C statistic, but I'm going to leave that as KS. Then if I come over to my assessment panel, we'll see the same pieces of information that we got for the neural network. So I do get that wonderful confusion matrix where I can see the true negatives and the true positives and their cohorts. If I do a right mouse button click and I click on lift, we'll see here that if we do focus in on the top 5th percentile of these customers, we get a lift from this model of about 3.4. So once again, that means if I use this model, I'm 3.4 times more likely to reach a purchaser in the top 5th percentile than just picking customers at random. And that does seem like a pretty good deal to me. I'll do a right click again so we can look at our receiver operator characteristic chart, and we can see that this KS statistic doesn't seem quite as robust as the KS statistic that we saw for my neural network. And you'll see that the cutoff is actually really low at about 1%, which is kind of interesting. So if we look at this misclassification, once again, it doesn't look like this is a very good classifier because it's doing a better job at non-classifications, but I think we'd have to modify our cutoff value in order to get a better representation and also get a better idea in terms of how we would want to use this particular model if we moved forward. I also want to show you, just like with the neural networks, if you click on the maximize button, you do get a nice detailed table that gives you all of the numbers, all of those statistics that you might be interested in looking at. So the numbers sometimes are hiding in this details table, but I wanted to point out how you could get them. All right, I think that's all I wanted to show you today. Thank you so much for joining me. Thank you for your time. If you are interested in taking a course in SAS visual data mining and machine learning, where we actually spend a total of 2 full days examining this software and building models and talking about the options and the inputs and the outputs, there's some information in the links below, and we'll be happy to reach out for you. If you have any feedback about the video, please feel free to leave it. We love comments and questions. And thanks. We'll talk to you soon.